Hey guys, so finally I'm back. I was getting a lot of messages on the WhatsApp as well as in the on my channel to discuss this very important topic. So finally, the wait is over. I'm here with you, joining with you all. Today we will be discussing this very important topic. This is a very important topic, as you know, that a lot of questions are being asked in the competitive exams from this topic. This is a very important topic, you know all. And today we will discuss all it is important nooks and corners of this topic. We will discuss it in detail. We will doing all examples and previous year questions which are based, which have been asked in the previous year exams and which are based on this. Okay, so you need to just give me at 20 to 25 minutes but full of attention, and after that you will master this topic. You will master all the questions. You will do all the questions in just a fraction of seconds after these 25 minutes. So let's start. I will be starting this topic with, you know, that how I start. I have a different way to start the topic. I will start with a simple example. I will be starting this with a query. Okay, so let's start. Suppose I have a carbon atom. Now I will tell you this carbon atom has a H attached to it. Then we have another H attached to it. Then we have another F attached to it. Then we have another F attached to it. Now I will tell you, my dear students, if this angle is alpha, if this angle is beta, and this angle is gamma, can anybody among my students tell me or or arrange these bond angles in their decreasing order? Okay, so I will give a couple of options: alpha less than beta, greater than gamma; B, alpha greater than beta, greater than gamma; or C, gamma greater than beta, greater than alpha; or D, beta greater than alpha, less than greater than gamma. So this is a simple question. Can anybody answer this question? So, in order to answer such questions where we do the bond angle analysis, we study the bond angles, we compare the bond angles in the entities, in the molecules, in the molecular world. When we do the comparison of the bond angles, we always need a very important concept that's called Bent's concept, and the rule and this golden rule is called Bent's rule. I will give you another example. I'm trying to understand you. I'm trying to make you aware of the thing that how important this topic is. Now I have a carbon atom. Suppose this is a C. Suppose this is a CCl bond. Okay, and we have another. Suppose we have another CCl bond. I have another CCl bond here. Now I will joining different kinds of atoms to carbons. Okay, to this to both the carbons. This suppose H, this is H. Now with this carbon, suppose I have fluorine, then I have another fluorine, then I have another fluorine. Now suppose this bond length is A and this bond length is B. Can anybody tell me whether A is greater than B, or B is greater than A, or A is equal to B? Which is the correct option? This is, isn't these questions valid? Yeah, absolutely, they are valid. I have another example. Tell me, this is N single bond N. This is N single bond N. No problem. Now this is H, this is H, this is H. Now here, this is suppose this is Cl, this is Cl, this is Cl. Now is this bond angle greater, bond length greater, or this bond length greater? Isn't it another valid question? Yeah, it is valid question. So how we will discuss, how we will get the correct options, how we will understand the actual order. So all these things you will master these things after 20 minutes. All these tells us all these things are occupied or inhibited, all these concepts are inhibited by this rule which was given by Bent, and it's called Bent's rule. Okay, so let's look at the statement of the Bent's rule. According to Bent's rule, orbitals having more s percentage, all those orbitals which have high s percentage, means we have which have a high contribution of s orbital, that's called s percentage, which have high contribution of s orbital, will direct towards electropositive substituents. All those s orbitals which have high s percentage, so it means that any orbital which has high s percentage will always like an electropositive substituent. It's not going to like electronegative substituent. It will always like electropositive substituent. But why does then theta will increase? Why? Is there any reason? Yeah, absolutely, there is a reason. And those all those orbitals which have less s percentage, all those orbitals, it means to say all those orbitals which have less contribution of s orbital, they will like electronegative substituents, and in them the bond angle will be less. So in order to understand this, let's take a simple example. So let's start. Okay, let's start this. Okay, okay. So let's start this topic, a very important topic, and with a very simple example, with very, I will like to refresh your concepts first. I would like to refresh your concepts, then we will start this. Okay. So as you know, I have teached you I have teached you chemical bonding. Everyone knows about chemical bonding, isn't it? Yeah, everyone knows about chemical bonding. Now in chemical bonding we discuss a very important topic called hybridization. Called hybridization, isn't it? Isn't it? Yeah. Now I will start with a very simple hybridization. I have sp hybridization, then I have sp2 hybridization, then I have sp3 hybridization. Now if we look if we observe these hybridization very closely, we come to know that when we do the bond angle analysis, we say any molecule which has sp hybridization has a bond angle of 180, obviously. And any molecule having sp2 hybridization without any which is a pure sp2, I mean to say no lone pair, its bond angle is 120. And any molecule which has sp3, pure sp3, it has 109 and 20 minutes. Okay, I will be taking the approximately equal to 109. But question is, have you ever tried to understand what actually what kind of drastic change occurs to the bond angle? What kind of drastic change occurs in these hybridizations so that these bond angles decrease so much? Bond angle is 180. There is a 60 degrees from when we go 60-degree decrease when we go from this to this, when we go from this to this, and further decrease when we go from this to this. But actually, why does the bond angle decrease? Actually, the reason is when we look at when we look at these hybridizations, when we look at them keenly, we say there is in sp there is 50 percentage of 50% contribution of p orbital. There is the contribution is more in sp2 clearly because it becomes 2 here. Then in this percentage of s percentage, sorry, p percentages even increases more. So why does the bond angle decreases? That is the question. But one thing we have to make in we have to establish in our minds is that ongoing from sp to sp3 hybridization, sp percentage increases. Now if p percentage increases, what will happen to the s percentage? S percentage contribution. Obviously, when we look at sp hybridization, overall contribution is 100, isn't it? Now, when we go to sp2 hybridization, now p percentage increases. Means in this sp, 50% 50 percentage is of s and 50 percentage is a 50% contribution is a p, obviously, because overall is 100. And if we look at the coefficients, it is one, so means it is equal contribution. It is a hybridization of equal contribution, where there's equal contribution of s orbital and p orbital. But when we go to sp2, the contribution of p orbital increases. Now when the contribution of p orbital increases, what will happen? Means s orbital contribution will decrease. And when we go to sp3 hybridization, the percentage contribution of p orbital increases further. So it means s percentage contribution decreases further. Now, what will happen when we go from sp to sp3? What kind of changes it will bring the decreasing percentage of s, what kind of changes it will bring. Let's do orbital analysis and let us see what will happen if s orbital contribution decreases. Now, when we do the orbital analysis of s orbital, we say that s orbital is spherical nature and p orbital is dumbbell shape. Okay, okay. It is a G rate. It don't have I, means center of inversion. It has a center of inversion. What does center of inversion mean? Means if we go from center to this, if the sign of wave function is positive, then we go back perpendicularly. The sign of wave function should be positive. S has this property, so it is called as a G-rayed orbital. Okay, now what will happen if the s percentage in any orbital increases? For that, we have to do the orbital analysis. And what will happen if there is percentage increase of s orbital, percentage increase of p orbital in any molecule? Okay, now note two things. This is a spherical in nature, and this spherical nature of S, it gives bulkiness. Note this point. This is very important point. You will get confused, but wait me and accord with me, be in peace with me for a couple of seconds, for a couple of minutes, I would say. Then you saying that s orbital is bulky, you will it will be you will say that to you it will look as a contradictory statement, but believe me, it is not a contradictory statement. I will prove it. Okay, now s orbital, yeah, sorry, p orbital. When we look at the p orbital, its contribution increases. The dumbbell shape of p orbital, what does this spherical nature of s orbital gives this orbital bulkiness. Note this point. Now, what will the dumbbell shape of this p orbital give to p orbital? Like, the sphericity of s orbital gives it bulkiness, the dumbbell shape of p orbital gives it longevity. There is no doubt in this. It is not contradictory. Okay, it will give it longevity. Go on. Okay, now it will give it longevity. Now we will go back to our topic, but keep these two things in mind. Please keep these two things in mind. Now, when we go to our hybridization, I was discussing hybridization somewhere. Yeah, here I was discussing this hybridization. Now, I told you that increasing s percentage increases what? Increases bulkiness, and increasing p percentage increases what? Increases longevity, means length. Okay, now when we look at the contribution of s here, it is 50%, so it has a high contribution, and more than 50% is not possible. Okay, in these three things. Now, when we have, it has a high s percentage, highest among all these three. The highest s percentage is in p orbital. Now, means in a, can we say that s orbital s percentage directly proportional to bulkiness? I told you that increasing s percentage increases bulkiness, so it means that it is the most bulkiest. Sp orbital is the most bulkiest orbital. When it's the most bulkiest s orbital, what will happen? The steric implications will increase. When steric implications will increase, the substituents or attached things, they will try to move as far as possible, and when they move as far as possible, then there is only one orientation while they can be maximum apart, and that is 180-degree bond angle. Okay, now when we go to the sp2 hybridization, the s percentage decreases. When s percentage decreases, it clearly says that bulkiness decreases. So when bulkiness decreases, they can be brought further close to each other, and the bond angle comes to be 120-degree. Now when we go to sp3, the bond angle still decreases because it has the least s percentage contribution. When it has the least s percentage contribution, so it clearly means that it has the least bulkiness. When it has the least bulkiness, means the bond angle will be smaller. Okay. Now come to our topic. Keep these things in mind and let's go back to our topic. Okay. Now, I have a f orbital, I have a sh, or I have a f atom, I have a h atom here. Now, when we look at the H atom, when we do the comparison of H and F on the basis of their electronegativity, there is absolutely no comparison. H is a element having 2.1 electronegativity, and F is the father of all electronegative elements. It has a electronegativity of 4. So is there any is there any comparison possible? No, absolutely not. Now, now, now F has a now F has a now F has a electronegativity of 4. H has a electronegativity of 2.1. Okay, okay. So when we do the orbital analysis of s orbital, what does s orbital say? S orbital has a property that it is most closest to the nucleus. We say that s orbital is most closest to the nucleus. Now, when we have the s orbital most closest to the nucleus, so can't we say that s orbital, anything which has highest s percentage will be highly acidic? Obviously, because it is the s orbital has a property that it's most closest to the nucleus. When it's most closest to the nucleus means it will any when we increase the s percentage contribution in any orbital, in any not in or in any species, in any entity, it will increase the acidity. Now I will cross check it. Okay, I will give you the C triple bond C. Okay, I will give C double bond C, and I will give C single bond H. Now tell me which one is more acidic. Okay, now we always say that acetylene is highly acidic. Why? Because it has a sp hybridization, means it has highest s orbital contribution possible. It is 50% s percentage. So the because since s orbital is very closest to the nucleus, so it keeps a very strong hold on its electrons. So leaving H positive becomes possible. Leaving H positive becomes possible. So it means that s orbital is itself an electronegative region. Note this: s orbital is itself a electronegative region, or we can say s orbital itself represents an electronegative region. So when s orbital itself represents an electronegative region, so can anybody tell me, we have a golden rule called like poles repel, unlike poles attract. Now note statement: s orbital itself represents an orbital which has what? Which has which s orbital itself represents a region of high electronegativity. S orbital represents a region of high electronegativity itself. It itself represents a region of electronegativity. Now come back to our question. Now I have H, I have F. Okay, F has very high electronegativity, H has less electronegativity. Now when we look at H has high electronegativity and H has low electronegativity. So H will prefer a region where there is less S percentage, isn't it? Or will H prefer that region where it has high S percentage? What do you say? Will F go to that region which has high S or low S? And will H go to that region which has high S or low S? Obviously, H will prefer that region which has high S, percentage. Why? Because H itself is not an electronegative region. Its electronegativity is less, so it will attract that region where S percentage is high. Unlike F itself has a very high electronegativity, so it will prefer a region where S percentage is very less. Because if it goes to a region where S percentage is very high, then because of its nature of being electronegative, there will be some sort of repulsion. It will be unstable there. So it means that in H, in a region where there is H, there will be maximum S percentage. But when we go back to what we discussed, I told you that increasing S percentage increases bond angle. I told you bond angle is directly proportional to S percentage. Now, clearly, from our concepts, in this region, the S percentage is very high. Now, when S percentage in this region is very high, it means that bond angle will be high. Alpha will be highest. Now, when we go to this region, this bond angle beta. Now, from this side, S percentage will be very less from F side, but from H side, S percentage will be high. So, at least from one side, it is getting a high percentage of S. From this side, is getting high percentage of S. So, from this side, since it is getting a high percentage of F, so at least second will be beta, means alpha will be greater than beta. Now, from this very, it will prefer less S percentage, it will prefer less S percentage, so gamma will be least. Gamma will be least. So correct option was option second. Okay. Now let us do another question which I told you. Look at this question. I told you, is this bond angle greater, or is this bond angle greater? Is this bond angle greater, bond length, sorry, is this bond length greater A, or is this bond length greater? Clearly, you will do this in the similar fashion like we did the previous question. This is chlorine, this is also chlorine, so this is not going to make any major difference. So what will make a difference is its attachments. Is its attached elements. H has a very low electronegativity of 2.1. It has an electronegativity of 4. So H will prefer a region of very high S percentage. So S percentage will be high in these bonds. Try to understand what I am trying to say. S percentage will be high in these bonds. So when S percentage shifts towards this to this side, so P percentage will be high in this side, in this bond. So I told you that a p orbital has a character that increasing p orbital, meaning increasing dumbbell shape, will increase longevity. What does longevity mean? Means length. So it means in this region, CCR region, the p percentage will be very high. Now when p percentage will be high, p percentage itself p percentage itself means length, means because of the particular structure of dumbbell shape like structure of the p orbital, it any increasing contribution of p orbital will increase the bond length. So since p orbital contribution in this side, in this CCl bond is very high, because s orbital contribution shifts to these CH bonds. So p percentage shifts to what? P percentage shifts to this bond. So it will be very, it so in this the bond length will be very high. So CCl bond will be very high in first one. CCl bond length will be high in the first one. Now look at the second one. This is a very high electronegative element, so it won't prefer s orbital contribution. So it will shift s orbital contribution on its opposite side, means s orbital contribution will be on this bond. It will have a high s percentage. Means high s percentage means what? It means bond angle. It means high bond angle. Second, it means high bond strength. Any orbital, any bond having high s percentage will be a strongest bond, will be strong bond, and it will have highest bond angle, but it will have least bond length, because bond length is inversely proportional to bond strength. Okay, got it? So when it will shift to, it is s percentage in this bond, so this bond will be very small, so A will be greater than B. So this is the correct option. Okay, I hope you are getting me. Now we will discuss another question. In the similar fashion, N single bond and H, we have another H and H. We have N single bond and we have this F, we have F, we have F, and we have F. So in the similar fashion, this is a this is low electronegative element. So it will prefer high H, high S. So high S percentage will be present in these bonds. In these bonds, S percentage contribution will be high. So in this bond, there will be high P percentage. So clearly, when it means P percentage increases, bond length increases. So this is, if this is A and this is B, then A will be greater than B, because here it is a high electronegative element. It is a electronegative 4, so it won't prefer high S percentage. It will shift S percentage in this N single bond N. So A will be greater than B. So what was the cracks of today's class? It was simple. It was simple to make you understand that on the basis of Bent's rule, on the basis of Bent's on the basis of Bent's rule, we can do two things. First, we can do bond angle analysis. Okay. Second, we can do what? We can do bond length comparison. Analysis as well as comparison. Now there is also a third parameter which we can do, that is called structural analysis. That is called structural analysis, and that is mostly done in a very important geometry, in a very important shape, that is called trigonal bipyramidal shape. I will give you a simple example. I will give you a molecule called PF4Cl, and I will give PF4, sorry, PF3. Okay, I will give PF3Cl2. I will give PF3Cl2, and I will tell you that its shape is trigonal bipyramid. But how will you make it? Let's make it. Suppose a student makes it like this: Cl, single bond F, single bond F, single bond F, and single bond F. Another makes it like this. Sorry, another makes it like this. See, like what? He makes it like this. Now, are both structures correct? Is A structure correct or is B structure correct? Or all, okay, or is this possible that both structures are correct? But I will tell you that out of these two structures, only one structure is correct. So which one is correct and how can we make structures? It is all told by Band's rule. According to Band's rule, any position where there is high S percentage, an electronegative negative element will never prefer such position. So let's do structural analysis and orbital analysis in trigonal bipyramidal geometry. Trigonal bipyramidal geometry. Trigonal bipyramidal geometry. When we do the when we do the structural and this analysis of these orbitals involved, we come to the conclusion that it is basically it is what is the what is we call the hybridization of this. Okay, okay, let's see. It is sp3d. Great. And the orbital which is involved is d z square. Great. It is d z square. Now, clearly you can see that 5 bonds are formed. 1, 2, 3, 4, and 5 bonds are formed in this. Okay. Now, when 5 bonds are formed, we say that out of these 5 bonds, when we study it properly, we say that 3 bonds are formed because of sp, sorry, not sp3, it is, sorry, it is sp, and 2 bonds, and 2 bonds are pd bonds. 2 bonds are pd bonds. I'm not understand. I'm not discussing it through the how does it happen. I have already discussed it on my channel and with all my students. I'm trying to understand you, revive you, all those things. Okay, it has 2 pd bonds and it has 3 pd bonds, three sp bonds. Now, when we look at the structure, we study that these types of bonds. What types of bonds? These types of bonds. These types of bonds. And clearly there are 2 types of bonds, this is one bond, this is another bond, and this is another bond. Okay, okay, great. Now this bond angle is said to be 120 degree, and similarly this bond angle is said to be 120 degree, and similarly this bond angle is said to be 120 degrees. But this bond angle, this one, it is said to be 90 degree, and this bond angle is said to be 90 degree. Okay, this is said to be 90 degree. So clearly there are 2 types of bond angles in this. One is 180, 120, and one is one, and two bond angles are 2 bond angles are 90, and three are 120. Now, I have told you that in this, out of 5 bonds, 2 bonds are PD and 3 bonds are SP. And it is said that these types of bonds, this, and this, and this, they are actually made up of these sp contributions. That means they are made up of only 2 orbitals, by mixing up only 2 orbitals, that is s and p. And these 2 bonds, they are made up of p and d. This and this, they are made up of p and d. And these bonds are larger. These are larger. Okay, great. And these bonds are shorter. These are shorter. Okay, why? Let's explain it. Okay, without taking you much of time, these bonds are called axial bonds, and these 3 are called equatorial bonds. Okay, great. Now, clearly, I will tell you one thing. In these bonds, equatorial bonds, since there is a clear contribution of s orbital, so since this bond and this bond has a contribution of s orbital, so will any electronegative element prefer this bond or this bond? Absolutely not, because I have already discussed that any orbital which has s contribution, any region where this high s contribution, then electronegative element will never prefer that position. So electronegative element will always prefer a position, a bond angle, a bond called axial bond, because it has p and d contribution only. So since it has p and d contribution only and no s contribution, since p has a property of high longitude, it has a longitude, means it will increase p percentage, increases bond length. So axial bonds will always be larger as compared to what? As compared to equatorial bonds. So always in such geometries, always put high electronegative species in a position of axial. So F will become to this position and not to this position. Not to this position. Because these equatorial bonds have S percentage in them. So S percentage means high electronegativity, means there will be repulsion. So F high electronegative elements will always prefer axial. They are they are preferring axial position always, not equatorial position. Okay. And since these bonds, these equatorial bonds have s percentage, and this axial bonds don't have s percentage, so I have told you that a region where there is s percentage, then bond and there will be high bond angle. Clearly there is bond angle 120, 120, 120, and bond angle is here 90 it because it is an axial bond. So since axial bonds don't have what? Axial bonds don't have s percentage, so a bond angle in them will be less. And equatorial bonds have s percentage, so bond angle will be high. So out of these two structures, which one is correct? Structure, this is correct and this is wrong, because in this structure Cl, which is a less electronegative comparatively when compared with F, it can't occupy axial position because it will destabilize the molecule. Since F, it has a high s percentage, it can't occupy equatorial position where equatorial bond where there is some s percentage, so F will actually go to this position and Cl will come down. So this was the basic idea of the Bendt's rule. And on this, we can do bond angle analysis, we can do structural analysis, and we can do what? We can do what do we say? We can do structural analysis, bond angle analysis, and bond length analysis. So now we will be starting Drago's rule. We'll do a couple of, I will take a short break up I will take a short break up 10 minutes, and we will start the pyqs on this topic, and then after that we will start Drago's rule. So just bear 10 minutes with